I'm glad to see lots of people. I'm also worried, so many people interested in atomics. Actually, you shouldn't do atomics. Go see Kevlin's talk about writing data concurrently, not do it. But anyway, if you're here, you probably want to know about atomics for just getting to know the standard better, or actually to solve a problem of yours. Let's see if I can enlighten you on what the standard says about memory orders in conjunction with atomics. Einstein was a really clever man. He came up with the theory of relativity, and to grasp that concept, he had to put away some really old, long-standing concepts and replace them with something new. And this is kind of hard to accept in certain circumstances, and we're going to talk about that in a moment. Beginning, some fine print. Guess you know these kinds of slides. Okay. Who has done atomics before? Can you raise your hand? Like, who has come in touch with them? Who has gone and seen Timo's talk about log-free algorithms? Cool. Oh, you've seen your talk. Great. Who has always wondered what these memory orders really mean? Okay. I'm glad there's some knowledge about atomics, because I'm not covering a couple of the basic details that Timo covered already, like the synapses of the state atomic template. I'm going to focus more on like what options do we have applying these things. Okay. Let's dive into physics. So Einstein observed a couple of things and thought about it and built upon some observations or some theory that the length of objects is not really given as an absolute thing, but it's relative to the observer. So if two objects pass each other at like a fraction of speed of light, like a substantial, like a fifth of the speed of light, then they appear shorter to the other one, maybe by 1%. And this is a problem because if you think about two things passing each other, and you observe the points marked A and the points marked B, you would think if the objects have equal length, they would pass each other at the same time. But now that the objects appear shorter because they're going really fast, if we are sitting like in the lower car and watching the upper one going past really fast, it appears shorter, and therefore the B's will pass each other before the A's do. But if we reverse this situation and look from the other car, then it's the other way around. A will pass each other before the B's do. So actually, there's no ordering in the events for A and B. And this is the relativity of simultaneity. Sorry, I'm a non-English speaker. It's quite a difficult word. And I'm also quite nervous standing here. Okay, so there's no total order of the two events in time. And in general, there's just no total order. And if you had this concept of a total ordering in time, now this is broken. It doesn't work. This model does not build upon this concept. So in a system with multiple moving things, there's no total order in time for events, the order depends on the observer. In a computer system with multiple cores running at the same time, there's no total order in time for memory changes. It depends on the thread. If this now scares you away, I'm sorry, but you have to be open to this when looking at memory orders, because that's what we need to deal with, and this is what makes it hard. We are really used to think things happen in a specific order, but they're not. I'm going to introduce this with a few examples in the beginning, and then I'll present what the standard defines as memory orders and what it does, with, in the end, a special focus on sequential consistency. Yeah, and then we're going to conclude the talk. I'll stop during the talk to take some questions, so I hope I can answer them as we go. As an example, when dealing with, we have multiple threads, when dealing with data visible to threads, what's like the simplest thing that comes to mind? Well, for me, it was like a reference counter, a shared integer variable that multiple threads change concurrently and reconcurrently and act upon. So let's try this. Let's take a counter variable, let it be atomic, and let multiple threads increment and decrement it 1,000,000 times. If we let this run with any number of threads, the result should be that the counter in the end should be 0 again. So what kind of choices do we have for modeling counter? Well, it could be an atomic. If we don't have atomics, what, like, we didn't have atomics previously. What shall we do? Mutex, yeah? Pardon? Int, plain int. How about plain int? Have we done so in the past? Yep. How can we improve on the int? No? Volatile. Wow, cool. Okay. Registered, yeah, okay. Now, let's say these are global variables. So let's say we try this program with a plain int, with an atomic int, and with the volatile int. Now, what is your guess? Is it going to come up with a final count of 0 if we run it with the plain ints? Anyone?
Depends on the architecture.
It's going to work. Yes, it works with the plain int. Success. Does it work with an atomic int? Ah, yeah, the hands go up. Yes, it works. Is it faster? Slower? Ah, slower, yes. So, volatile int. Does it work with volatile int? Few people. Come on, works with plain int. Why not with volatile int? Does it work? Doesn't work. It's faster than atomic, but it doesn't work. Ah, snap. So what's wrong? It works with plain, works with atomic, but not with volatile. It was a trick question, right? Why does it work with plain? Yeah, there's no code generated because the compiler can see adding 1,000,000, subtracting 1,000,000, no code generated, works all the time. It's really fast. So atomic works, yes. Volatile works, no. Why does volatile not work? I thought like volatile, like on an Intel platform, it's all atomic anyway. What's wrong? It's not atomic. Why is it not atomic? Because the instructions that comprise access to a volatile int are just not atomic. They are reading from the memory, incrementing it, and writing it back. And without special care, it's not atomic on Intel. Although reading an int, or just reading, is an atomic operation all by itself on Intel.
I can put +lock and do a memory index increment, but I can't get access to the assembly instruction from C++ unless I use as an. Sorry.
Yep.
You can make it.
Yeah, kind of hard. Okay, so I'm just inserting a slide about conducting these tests. As we just saw with the plain int, it was optimized away, so you need to take that into account when doing these tests, as well as certain other things like aliasing, where the optimizer will produce different code whether dependent on whether or not it can figure out whether two variables refer to the same location or not. This is an issue by indirect addressing through pointers and references, right? You might want to take into account placing your variables in memory. Certain cache lines, if they end up in the same cache line, it's going to be different than different cache lines. You need to think about scheduling of your threads from the US and doing actual time measurement, what you're actually covering with the measurement. But I'm not going too deep on this, because I'm more trying to explain the results. There are lots of tests doing these out there. You can find lots of material on it. So I'm just trying to discuss the results. So what was the problem with our initial experiment? Why does the volatile actually have a problem? It's not atomic. It's not atomically incrementing the count, but the actual problem is that multiple threads do it at the same time. And they could end up interleaving their instructions. They could fetch the integer. Each one of them increments it and writes it back. So there's only been one increment in total, where there should have been two. And when decrementing, they get all confused. We just don't know. So it'll all be fine if you just do one thread incrementing two counters and let others observe what's happening. I'm naming this chasing counters. If we start with 0, we have two variables where the later one can never be greater than the first one, right? We only have one thread running this program, and others observe this and try to figure out whether B can actually end up being larger than A. Hopefully everyone agrees that by looking at the source code, it shouldn't be the case that B could end up larger than A at any point. Yeah. Oh, we can vary plain int, volatile, or atomic. They both start at 0, and we have one thread incrementing them in a loop. Yeah, we increment A from 0 to 1, then increment B from 0 to 1. Then we loop, increment A from 1 to 2, then B from 1 to 2, and then we just continue, right? And we have other threads reading these values and trying to figure out what they get. Yeah?
You're making the assumption that the optimizer has reordered them, and it could be. And therefore, B could be larger than A, depends on what the optimizer does.
Yes.
Normally, it will probably not reorder.
Cool. So, trying this. Plain, it's a no-op. Okay, it's optimized away. Atomic works. Volatile might or might not work. If we make it volatile, we essentially tell the compiler not to optimize the code and not to reorder it. But still, we figure that on a certain architecture, different threads can still observe the updates in a different order. Now, this is somewhat connecting to the initial example with the cars passing each other, where the events A and B might end up in any order, right? And while we don't observe it on an Intel platform, we might observe it on a different platform, which I forgot to unpack. Tried it on a Raspberry Pi, which is a 4-core ARM architecture. It doesn't work here. Does not work. It's a popular architecture, and you need to be aware when porting code, especially from Intel to somewhere else, you might end up with code that's not working. So in a broad sense, we can categorize architectures in terms of consistency and say they are strong or weak. So the Intel architecture and the 64-bit architecture are strong. And Spark has, by now, with the modern processors, also a strong consistency. But there are more nuances to this than strong or weak. That could fill a whole nother talk. So I just simplify it to strong or weak. And the ARM architecture is weak. So actually, we end up with this concept that certain events can end up in a different order at the same time, basically, when viewed from different threads. Yes? Yes. Yes. I didn't. I said them read B and then read A. And if then you end up with B still being larger than A, then something's wrong, right? So in certain threads on ARM, they just observed this, I say, failure case. We didn't intend this to happen, but yet it did. Itanium is the Intel 64 original architecture. They meant it to be weak, but they lost against AMD with the 64 AMD architecture, which is now termed 8664. So another quite professional architecture is PowerPC. Is also weak. So if you happen to have access to one of those machines, you can try it there with loads of threads, I guess, loads of concurrency. So these are the things that we need to take into account when dealing with atomics and exchanging data in memory with other threads. Okay? So when we write a program, we put things in the source code, which I now name source code order to distinguish it from program order. The compiler will take your source code and turn it into assembly, which then forms a program having instructions in program order. These are fed to the CPU, which then turns them into the execution order, because modern processors have a notion of out-of-order execution, where they will on-the-fly rearrange your memory access and instructions without asking you, basically, come up with an execution order. They will issue writes to memory, and then the memory system might still distribute this information across the whole system, among the other cores, among the other threads, and they can, each of them, observe the writes in their particular order, forming the observed order for each one of them. And at each stage of this, we might introduce bugs in terms of logic for our program. So if we don't advise the compiler by means of certain instructions in the source code that certain things in our memory accesses should have a certain order, then it cannot tell or write that to the program and in such a way tell the CPU not to reorder accesses. And the CPU cannot make sure the memory system will have flushed the information in a certain order, which is what atomics do with equipped with a certain memory order. So this is what we're talking about. A plain volatile will never do this. So I hope by now you all agree that we cannot use volatile to safely exchange data between threads. Next up is introduction to and explaining the semantics of the memory orders. So are there questions so far? Okay, very good. So how do we instruct a compiler that certain things should go in order? if we look at a single thread executing either of these sequences of statements and look at the standard, then we should come up with like, okay, I'm incrementing A and then I'm incrementing B, or I do it all in the same instruction. Where's the difference? The difference is what was called the sequence point prior to C++11, which is now called sequence before. And individual instructions are sequenced before their next instruction or statement. And the standard says that by the end of each statement, all its side effects must have completed before beginning the next statement. So the upper bit should complete incrementing of A before trying to increment B, and have that done before computing A divided by B and do something with the result, return or whatever. Whereas the combined statement will not have this restriction, so A and B have no ordering, they are not sequenced before each other. But how does it help us? What does sequence before mean? If we think that incrementing A will have completed before incrementing B in the sense of other threads can observe these writes in memory or to memory in the same order, we are wrong. The sequence before relation between statements is only true within the thought of abstract machine of executing a C++ program in a single thread. So sequence before does not mean that any writes become visible in memory to anyone else. For A and B being different variables, we could think of incrementing both of them by loading a value into a register, loading another value for A and B, incrementing both of them and writing them back, thereby interleaving the instructions. The compiler is allowed to do this for the combined statement, but not necessarily for the first one. If the compiler could figure out that A and B are actually different variables in different memory locations, then there's actually no difference between these things. It can then interleave incrementing A and B, just like the statement at the bottom. But if it can't figure out that A and B are different variables, then it needs to assume that writing to A will affect the content of B. Therefore, the first example has defined meaning in terms of the standard, because completing the side effects on A will then have an effect on B. But it's only within one thread, right? It does not mean that these writes need to become visible in memory. So sequence before replaces sequence points, but still focuses on one thread of execution. And it only affects compiler optimizations in generating assembly on that. It does not mean anything in terms of writing to memory. Yes, to repeat that, if A and B actually refer to the same memory location, the same variable, then the statement in the bottom has undefined behavior because it's concurrently, not talking in terms of thread, but in the same statement, modifying the same memory location, which is undefined behavior. Yes? Is it unspecified if there are separate variables? So what is specified? If A and B are different variables, it's well defined what's going to happen. Yeah, so you need to take that into account, especially when doing tests, because if you can provide the compiler with the information that A and B are different, then it can produce better code, faster code, basically, which is the whole point of aliasing. Okay? Sequence before, it's all within one thread. All right? So, sequence before is one of the terms that comprise explaining memory orders in the standard. Another one is synchronizes with. This one spans multiple threads and says that certain operations in one thread synchronize with certain operations in another thread, and then some other wording explains what becomes visible if two things synchronize with each other. I'm going to show you, don't worry. And if you combine both ideas, then you can explain what happens before means, which gives a partial order to things that happen before others, and therefore give you a visible side effect of one thing happen in one thread, make it visible to another thread. Okay? These are like the terms. And let's apply that to a simple example where we do data parsing. We have a plain non-atomic data, let's say an integer, but it doesn't really matter what we have, and we populate it with some result that we computed. And then we want to give this information to a different thread by means of a flag, which I call done. In this case, it's an atomic of bool, and we set it to true. And if the other thread observes, oh, it has changed to true, it's going to read the data, assuming that the data is now valid. But it doesn't need to be valid. The terms that we need to apply here are the first thread writes to the data, yeah? So these two instructions go in the first thread. It writes to some memory location and then sets the atomic. And because writing to the memory location is sequenced before writing to the atomic, and then writing to the atomic synchronizes with reading in a different thread, and then this reading is sequenced before evaluating the data, we have a happens before relation where writing to the data becomes visible to reading the data. And this is now bringing into relation an atomic access with a non-atomic access, which is actually what we do, because not all of our data will fit into atomic variables. If all you want to do is pass a single integer, and this comprises all of your data, you just use an atomic int. But most of the time, you're going to write to memory lots of data, and then tell someone else, go ahead and evaluate it. Go ahead and read it, I'm done. You can now do whatever you need to do. And for this to work, we need a synchronizes with relation somewhere in between. So writing of the data comes sequence before, setting your atomic. The atomic synchronizes with reading the atomic and observing this value. And this is sequence before in the other thread with evaluating the data. Okay? So synchronizes with really gives this inter-thread dependency. And the thing to watch out for is that whatever value we load needs to be the value that was written. If we load too early, we don't see the value written, so it does not synchronize, right? But then we would return false and not go ahead and read the data. We wait for it to return true, and thereby we read the value that was written previously, supposedly, by someone else. And only in this case, these two synchronize with each other. Make sense? Yeah? The question is why writing to the data up here is sequence before storing the atomic. Sequence before is really the order in your source code. If you lexically write this above writing to the atomic, then it's sequence before. If the done was not an atomic, it would still be sequence before. The optimizer would be free to reorder things. True. But if, yeah, I'm seeing your point. So if done was not an atomic, then the optimizer would be free to reorder these things. But because done is an atomic, and because we apply certain memory order to it, the compiler is not allowed to do this reordering. But we are going to look at the memory orders now, which make a difference. Sequence before is orthogonal to optimization. Yes, sequence before is just the concept of side effects that no matter how they are evaluated in the end, are just giving you guarantees to do logic in your source code. Okay? So sequence before will not mean the optimizer cannot rearrange these things, but the atomic will mean the optimizer cannot go past beyond this point, right? I'm going to cover this in a few slides, actually, but I know this is part of the confusion, like what does it do? Why doesn't it apply all these things? Okay, so I didn't yet explain what MO is. It's an argument to both the store and the load operation, and it's short for memory order. Okay, memory order. What is memory order? It's really just an enum in the standard namespace with a couple of values, and we can choose from these values. Not all values are applicable for both store and load. Yeah, but we'll cover all of them. So we have memory order relaxed, which usually goes by itself and doesn't impose any ordering. We have consume, acquire, and release, which kind of like form two pairs of operations, which is consume and release, or better, release and consume, and release and acquire. We'll be looking at those two, and there's a combined acquire and release. Yeah, you can guess it's release and acquire for things that are both a read and a write. And then the sequential consistent memory order, which is abbreviated as well, which is the default order and the strongest one. It's a default order applied to all of the operations if you do not specify any memory order. So if you don't care about memory orders, you just get the strongest ordering, and hopefully everything will be fine. If it's not, then there's no other memory order that can come to the rescue. Okay? So looking at the example and applying relaxed ordering, yeah, we've lost because relaxed ordering does not imply synchronizes with. It does not imply any ordering, which is why it's called relaxed. All the others do, but relaxed just doesn't. So for relaxed store, it does not synchronize with the relaxed load, even if the load would observe the value that was stored. And therefore, we cannot rely on the data be visible that was written previously, because we don't know if it was written previously. For the relaxed ordering, the compiler could actually reorder things, because relaxed only applies things to this atomic that you work on. And it just ignores all memory order whatsoever. So basically, if you're just passing data contained within the atomic, that's fine. But if you want to make any other data visible, it's not fine at all. It's not going to work. Yes?
So I get that this allows the assignment data to be executed after the store.
Does this allow the assignment to data to be executed after the store? Yes. You're missing the idea behind synchronized with. Relax does not have this. The others do. Wait a moment, and then if this doesn't answer your question, okay.
It's not related to the data before.
It's not
related to the instruction assigning to data being reordered.
Is synchronizes with orthogonal to data being assigned or reordered after the store. They have certain relation, but not for relaxed ordering. So relaxed ordering will allow the assignment to data come after the assignment is done. Okay? By whatever means, by the optimizer reordering instructions, by the CPU reordering instructions, or by the memory system not distributing the updates. However, there's no ordering guarantee. Therefore, we cannot read the data in the end. Okay? Okay. Relaxed semantics just provide atomicity for this atomic variable, but no ordering whatsoever on all the other operations surrounding this atomic. Okay. So relaxed semantics will work for the initial counter example because it's just the counter. There's no other memory location that we change or pass. It's just the counter, and incrementing the counter atomically will prevent it from being gobbled up by multiple threads, which is why it's slower than using a volatile int, which was messed up. All the threads need to wait for the atomic operation of the other threads to complete before applying their own. Relaxed semantics. Okay, let's talk about the next one. Release acquire or acquire release. If we do the same store with release memory order, we're telling everyone, the compiler will tell the CPU will tell the rest of the hardware, that storing data needs to come before storing the flag. And the sequence before, like what we do in our source code, everything that we in our source code comes before storing the flag will become visible to others. This is sequence before. This is what we do in our source code before storing the flag. Once we store the flag, all the accesses we specified before, basically, because we're not actually doing them in the source code, the program will eventually instruct the CPU to do it, and the CPU needs to instruct the memory bus to do it. All these operations are guaranteed to become visible to the other thread who is observing the stored value from the atomic variable. The other thread needs to load the value applying the acquire semantics, the acquire memory order, which means give me all the data. Give it to me. I need to see it. So we've talked a lot about reordering writes after storing the flag, right? After the atomic store. But also, we cannot reorder the reading of the data before loading of the atomic. We could do, that's an optimization as well, prefetching of data. But we must not apply this if there's an atomic access acquiring memory. Okay? So this is like the counter optimization to like do later writes or earlier reads. And neither of them must happen when applying release acquire semantics. And this is, well, the semantics for most of the data passing cases. I would say it's like the default, I'm passing data along, let's try release and acquire semantics. So this example works, yes.
But that doesn't mean that later stores could not be pushed before or later data.
This does not mean. Right, the question is if I, in the first thread, have any stores or any writes to memory after storing of the flag, these might still be reordered before the atomic store because they don't play into the game here. They're unrelated, right? So the release semantics just say previous stores cannot go past this point. No writes can be ordered after a releasing store on an atomic. Everything before, everything like sequence before, needs to be covered by this store. Okay? Any other optimization, like bringing other writes up and do them earlier, it's not forbidden, can happen, whoever does it. So releasing prevents writes from being reordered afterwards. And acquire semantics prevents reads from coming before the acquiring. We need to wait with the read until we actually acquire the value from the atomic, which then by logic implies the data has become available and we can observe it and fetch it from the memory. Okay? Does this make sense? Cool. Of course, this is a stronger semantics than the relaxed one, and it will work with the initial counterexample. Right? Everything will work with the initial counterexample. But I'll have other examples where we apply this and see that it makes a difference to relaxed semantics. So, next one up is consume. It's still the same release store that we do, but we're going to take a consume instead of acquire. So instead of acquire, we can consume memory. Release, we've talked about. The writing of data will become visible or will not be reordered after the store of the flag. But the consume does not acquire all of the memory content. It will only consume dependent reads. And because done and data are two independent things, and reading of them is independent from one another, which is why we can think about reordering the reads in the first place, there's this idea of consume semantics, which does not work here. As consume says, no dependent reads can be reordered before the load. But because reading of data does not depend on the value we read from the atomic, it's not a dependent operation, and therefore there's no ordering. So how do we need to change the example to make a dependent read? If instead of storing a flag true false, we store the address of our data, then the reader can get the data from the atomic variable, the pointer to data from the atomic variable, and then go ahead and dereference that pointer. And it's somewhat clear that you cannot go ahead dereference the pointer unless you actually have the value of the pointer, right? And therefore, supposedly, hopefully, we can have an improvement where we don't need to issue like heavy memory barrier instructions to the CPU, because hopefully the CPU cannot reorder reading of some pointer unless it has the pointer value, right? So therefore, we can assume that the CPU cannot reorder by itself reading of the pointer D before reading the atomic. This is like an implicit ordering. But still, there are CPUs that do this. Like, they would observe the value from the atomic, but not go ahead and fetch it from memory because they have an older version of that memory in their cache. So you get like the older value, but still having a dependent operation. But then it's the compiler that needs to prepare your program to run on this platform and needs to know about this and issue instructions for the CPU to invalidate the cache and go ahead and fetch the memory again. Yes?
As I understand it, when you have the previous slide, consume and you pass the Boolean flag.
Yes.
As I saw it in your consume operation, thank you, there was no sequence before between the data being typed to cout and the done.load. There's no sequence before hence the .line.
Oh, the question is, well, here, I supposedly don't have a sequence before relation.
As I see it, whereas if you look at your lexicon,
Yes, actually, that's not what it should mean.
yeah,
It's still sequence before, but it's not a dependent load.
right.
So it's still, this one, a sequence before this instruction. But when applying the consume load, it says you can only observe data that depends on the value of your load. So actually, because the compiler sees that done and data are different things, they do not depend on each other, it can now still reorder reading of data before the if. Because it's consume load. If it was an acquire load, it could not do this. It was disallowed to do this. But now it's in consume load, therefore, the restriction does not apply and it can reorder these instructions. Or if we think further, it still might output assembly, where in the assembly, in the program order, reading of data would come after the load of the atomic, but then the CPU would say, oh, these are two loads. I happen to have the data in cache for some reason from previous times. I'm just going to fetch the data and not wait on the load of the atomic. But now in the revised example, this should not happen because it needs the pointer from the load, right? But then there are architectures that don't actually check whether there's an updated value in the memory. Yes?
So the difference between wire and consumer side. No memory was in order for the wire, and no dependent memory was in order for the consumer.
Yes.
The question is, can you give a clear definition of what dependent read is? How to actually define it? Because I think that might be unclear.
The question is about what actually is defined to be a dependent read. Go look at the standard. There's like this paragraph on, oh, anything, like if you have a variable and you name it later in some operation, then it's going to be dependent unless it's like one of these logical operators, one of these conditional operators, like in these circumstances, and it can't be an index, it can't be whatever. It's like, I didn't put it up on the slide, but there's like this block of what comprises a dependent read with lots of exclusions. But hopefully, or maybe not, this is not going to be of much interest because the consume memory order is discouraged by the current standard. Because implementers figured that they can't necessarily do better than acquire, and acquire is stronger. So you could try to optimize your program to make use of consume semantics, but you basically waste your time trying to figure that out instead of using acquire. And your implementation doesn't make any difference between them, so why bother? So yeah, the constant seems to be that since there's no implementation that can substantially do faster using the consume semantics, don't use it. It's more complicated, and you don't get any benefit. Yes?
But theoretically, the consume might invalidate a single cache line rather than acquiring all stores to invalidate all cache lines to make all writes or read physical.
The question is, the consume semantics could, in theory, be faster because the CPU does not need to invalidate all the cache and refetch all the memory across all the cores. Yes, but even for acquire semantics, it does not necessarily need to invalidate all the cache and reload everything for all the cores from all memory.
The reason why is because processors in a processor architecture have a FIFO, the store FIFO, and the stores being committed to the L1 cache and to low-level cache in main memory. It goes into the store FIFO. Therefore, all stores are implicitly ordered. There is no known architecture that does not have, superscalar architecture that does not have a store FIFO. And therefore, consume semantics implies you don't bother with store FIFO. Forget it. They will have it. It's pointless. It's not implemented in hardware.
In theory, it could be faster, but there's no implementation out there that makes use of it. That's like, yes, we would need to produce some hardware to make it faster.
Not even exotic supercomputers omit early store FIFO because it's just such a blindingly prolific package.
Does that answer? Okay. So don't bother about consume. All right? I'm not going to mention it for the rest of the talk. So if you have any questions about consume, go ahead. Okay. It's not deprecated, it's discouraged. But it's under revision. The standards committee is thinking about rewording the standard at this point. And it might turn out to become deprecated or be removed or be improved. We don't know yet. Cool. So this is the consume. And now we apply the memory order to a revised example. So we have the chasing counters again, but we're going to drop one of the atomics. So we are going to mix a plain integer A with an atomic integer B. And we want the increment of A to become visible when incrementing B, right? Because it's in the source code before incrementing B. And for incrementing B, I now use the fetch at member, which takes a memory order, while the operator ++ applies the sequentially consistent memory order. But then we can't change it. So we're going to change the memory order MO on incrementing B. And now we still have the same setup that lots of other threads try to observe B and A and figure out whether it makes sense or not, whether they come in order or whether B gets larger than A. Okay? And it turns out relaxed semantics don't work anymore, but release acquire work. Because when incrementing B, we apply, it's a store, there's also a load, but we apply release, and that means the write of A needs to become visible to whoever is reading that particular value of B. And therefore, we rule out the possibility that anyone can observe B being larger than A. Whereas with relax, we can't. Okay? And of course, it's going to work with sequentially consistent because that imposes more restrictions than acquire release. Make sense? Cool. So, do you have any more questions about memory orders other than sequentially consistent? I'm calling it with release, yes. For memory order, MO, we can apply all of the memory orders. Release is only valid if your operation is going to write to memory, which the increment does. And acquire is only valid if you're actually loading a value, which this one does as well. So the fetch add is actually loading and storing a value. Therefore, it's a read, modify, write operation. And therefore, I can work with release, acquire, and release acquire memory order. But we really care about the release. So we can use either release or release acquire as an argument to this operation to make the write of A visible to others. To change this example, I could have used a local variable B underscore to keep track of the count and then just issue a store into the atomic. Therefore, I wouldn't need to read the atomic, increment it, and write it back. I would like increment a different count, like in the local register, and then just store this value to B. And therefore, B would be increasing as well and would equally work. Okay. Any other questions before I get to sequential consistency? Okay, sequential consistency. This is the strongest memory order, and it's applied by default to all operations. It's doing a great job in this particular, it's making your life easy, basically. You just get strongest thing with the most restrictions. But we saw that release acquire semantics are good for data parsing, so what does sequential consistency do differently? I've now basically a variation of the example where we're parsing data, but I've introduced a third thread on the upper right, which tries to write some other data and also write a flag. Just to motivate what an atomic means when we apply operations to it. So we assume that the thread on the upper left wrote some data A and then set the done flag to 1, which is now, I turned it into an integer to distinguish between the two threads writing to it. They're going to write 1 or 2. But if the reading thread observes the value 1, then it got its value from the upper left, right? So it's reading 1, and therefore it can only rely on data A being available. If it read a 2, then it could read data B. But because it read data 1, this load synchronizes with this store. And the thing we can't observe is storing the 2. If you think about it, it doesn't really help if you actually put this into practice. Because if you don't observe the 2 being written, because it could happen concurrently with writing a 1, then you're losing on one of them. You either get a 2 or the 1, and you don't know, because you never have read the other value, if it had been stored actually, or if this thread is still processing whatever it's doing and hasn't stored the value. So in this sense, we can assume that the storing of the 1 and reading of the 1 are somewhat close together, and storing of the 2 cannot go in between. Right? If this one went in between, then we would read the 2 instead of the 1. So all we know is like it has been written before and we didn't observe it, or it hasn't yet been written. But it cannot go in between. So there's an order of the operations on the atomic. And therefore, because we can't figure out whether the 2 has been written or not, it's not useful. That just shows that we have some sense of order on the operations of this flag, this atomic. Okay? Does that make sense? So the modifications on an atomic actually have an order. The standard says the program needs to behave in a way that an atomic is modified, all the modifications have a total order. How you put that into practice, well, it's compiler implementers and hardware manufacturers doing this. But the mental model is there's a total order of all the operations on one atomic. But the catch is, it's one order per atomic. So the orders of modifications on 2 atomics don't relate to each other by default. They're totally independent. I have 2 things that I need to cover. So first, the order of one atomic. Say we had 3 threads, and they applied different operations to the same atomic variable. Then these need to go in order, and whatever we can observe in the end when we acquire a value from this atomic is whatever was the last release operation, and basically anything before depends. So suppose thread 1 wrote something to memory and then did a releasing store to one variable like we had in the example. Then it could still apply more atomic operations on this variable, which for a single thread are ordered by the sequence before relation, right? It could do a relax write, and the thread T3 might or might not observe this. But it doesn't matter, because all the previous stores that we released will become visible. All the memory that we changed will become visible. And it even becomes visible if another thread T2 would apply read, modify, write operations on this atomic. Whether or not they would be relaxed or acquire release. But actually, if the fetch add in between would be a releasing store, then we would lose T1's information and only be guaranteed to see T2's information, because whatever we acquire only goes back to the last release. Therefore, read, modify, write operations like fetch add can have acquire release, which acquires all the things that thread 1 has done, and in addition releases all the things that thread 2 has done. Right? And by this release, all the memory, including T1's modification, will become visible to the acquiring load. But if the fetch add was a relaxed operation, then we can go back to the last release operation of thread 1, and thread 2 would still modify the atomic, but not make visible its changes to memory. Therefore, whatever we acquire is the last release operation. And whatever that covered in turn. Okay, makes sense? Yeah, tough one. Okay, so this is the order of one atomic. But if we look at two atomics, A and B, and different threads, they could really have a different idea of the contents of these atomics. While each atomic has its own order of modification, which is a total order, they don't relate to other atomics. This is again related to the physics example where we don't have a total ordering of two events taking place, because these are two different atomics. And even with acquire-release semantics, there's no interaction between different atomics. Uh-huh.
What happens if atomic A, if I have the shared variable in C, and atomic A loads the address of C, and does some kind of reading of the contents of C, atomic B likewise loads the address of C and does a reading. Surely then there is an actual order between them because I've introduced the data dependency on C, the address of C.
So you're saying if two different threads each stored the address of a common variable C into their atomic A, respectively B, and someone else would observe these values?
I observed it. So your thread atomic A, your atomic A thread, you reference the contents of C after it's done the loading. And likewise atomic B, you reference that thread, you reference the contents of C after B has done its atomic load of the address of C. Surely
So you're saying two threads, one of them observes an address of the variable C, loads it from atomic A, and the other one loads the same address from atomic B, and then they go ahead and dereference this address.
Yes.
So you could observe.
Surely then there's an order now, an implicit order between the two because of the dependency on the address of C.
You're saying this will introduce a dependency between A and... I don't think so, it does.
Because I thought when you give the acquire release and the order that we're told to forget about, which shall not be named, beginning with C, right? You introduce the data dependency by passing the address of C. To the address.
I introduced in a previous example with a memory order that we're not...
The one that we shall not name.
that one that we shall not name. If I load an address from an atomic, then hopefully someone has released some data at this address for me to observe. But two different threads observing the same value from different atomics do not have any dependency between each other. They just happen to observe the same value in their respective atomic. If they both point to the same data. That still does not tell you who sees the contents in the atomics. They still might act up on whatever data you filled and passed, but while one thread may observe A being empty and B having this address, the other thread may observe it in reverse, where it can observe the address in A, but not in B. B still be empty. I have an example coming up for that, hopefully. Okay. So we see here two threads have different ideas about the modification of these atomics. They somewhat contradict, right? For our usual notion of there's a total order of events happening in memory. But here, they're somewhat reversed, and therefore they would contradict. Yes? Oh, I'm sorry, yes.
So every last square is like an operation that modifies atomic A or atomic B?
Every square is an operation that modifies that respective atomic variable, and time passes on from top to bottom. So this is depicting the order of modification on those atomics.
Who's modifying them? Is that T1, T2, or is that another?
Who is modifying these things? Someone else.
T3.
T3, T4, until up to T100, someone else. Someone's modifying it, and we're just observing from two different threads and observe like contradicting things. Oh, right. Good point. I'm not saying they are modifying these atomics. Yeah, I should. Didn't come to my mind because it was clear to me what I was trying to say. So we have two shared atomics, A and B, each of which are being modified from some threads we're not going to look at that are not on the diagram. So they have some modifications, and for each of them, they're put into order, into a total order. So we have these squares depicting the modifications of these atomics and the order in which they occur, with earlier ones being further at the top and later ones being further at the bottom. And then we have two threads, T1 and T2, who just read these values, right? And if they read these values, they're going to read some last written value from that atomic. But last written is relative to this thread. So whatever T2 reads from atomic B happens to be a newer information than what T1 can access. Does that make sense? While at the same time, for A, it's reversed. So it could be a system where T1 and T2 run on different CPU sockets, basically, and some information hasn't passed from one to the other. So there's a certain delay. But it depends on the computer system, how it's, what restrictions it imposes. Like the strong consistency models will not come up with this. Yes?
So I think, just try that all we're saying, we are just witnessing the fact that within the thread, the atomics are, the reads to these atomics are sequenced before, but that doesn't mean anything in the cross thread.
The question is, while within each thread we can see that accesses to atomics are sequenced in some source code order, and this does not imply any ordering on the values we observe. Cross threads, yes. Yes. So even if in one thread reading of B comes after reading of A, it might still read an older value than some other threads reading both of them. It's like there's no ordering between different atomics by default, right? So they could observe any of the values in the modification order, even if it was an old value, and while the other one reads a new value. It's like, I'll try to make that clear with an example on how it can go wrong, some sort of, yes? There's an order on the thread that is executing these things. The order is not with the thread, but with the atomic. So for every atomic, the modifications have some total order. So if it was like increasing a counter and someone read 5, then it can't later read a 4, right? Because that's previous in the modification order. And you can read a 5 here and a 5 there, but then someone else can read a 6 here and a 3 there. But how does that make sense? Like if I got the 6 here, I should have been at least able to see the 5 over here, but it's not. So one thread sees 2 5s. How can someone else reading a 6 here get an older value over here? But it can. So each thread has like, maybe explain, like a pointer into the modification order, and it can advance along the modification order but there's no synchronization between two different atomics. The order in which they happen does not depend on the observer for, there's an order per atomic, not per observer. But the observers progress differently in each of the orders. So it can be like getting real slow updates on one of the atomics, and other threads can have newer values already, while on the other atomic it can be really fast, and the other ones are waiting for new values to appear. So in that sense, updating the atomics don't have a total order, because that order depends on the observer, yes. It's inter-atomic. So across the atomics, there's no synchronization. Like if you've read a certain value here, you need to, you can't see all the values over here, but actually you can see all the values. So yes, A can happen before B, and B can happen before A for two different observers, like T2 and T1. But still, for any single atomic, they cannot go up and down the order. They can only progress along the order. This is the total ordering on single atomic. But no one tells how far they are in reading this modification order. They can be stuck at some point, and others can have already advanced, or they, yeah, there's no order, and there's no restriction on like get rid of old values. You need to see new values.
So like in this example, let's say an extreme line would be like another observer thread that is watching the last line of communication on the bottom, and also is watching at that point is when you see the first one back on the.
In an extreme case, yes. 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 So in an extreme case, an observer can see the latest value of A at the very bottom and still have the earliest value of B. But from then, it can only see newer values of B appearing, and it can never go back to older values of B nor of A, right? It's only progressing downward. Yes? Writing counts as observing. Writing counts as appending something to the atomic, and then you can never see all the values. If you write an atomic, then you can be sure that whatever values you read afterwards from this atomic are more recent or are your value. Okay, yeah, that's really difficult. So what does sequentially consistent do? Well, it resolves all these problems, because if we apply sequentially consistent to some of the modifications, then we have a set of sequentially consistent modifications. And all these need to go in some order. So if the red squares now depict writes to the atomic within the memory order of sequential consistent, then all of these operations participate in some total order that must not contradict any of the particular orders, nor any of the sequence before for a single thread, right? So in this sense, if we do sequentially consistent modifications to atomic A and B, which don't need to happen from the same thread, they can be from totally different threads, like from 100 different threads, but each sequentially consistent modification will end up as some square in the order for a particular atomic, right? And all these modifications now need to go in some order. a global total order on all of these operations. If all we do is sequential consistent ordering, if we never apply release, relax, acquire, whatever, then we have this single total order of all modifications. If we mix and match, then we end up with some operations being sequential consistent, and only those then participate in the total order. So if in this example we have a couple of red modifications, then we see it contradicts reading for T2, because if it actually observed a newer value for B here on this end, if it observed this value, which comes after this value in this modification order, then it must not read any value for this atomic older than that red square. It at least needs to see that value or a newer one. Does it make sense? So if you only apply sequentially consistent memory orders, then you restrict on seeing all the values. If you mix and match, well, you're somewhere in between, but at least you can't go back beyond the last sequentially consistent write on some atomic. But still, you don't know what the global order is. Your logic, like sequence before, or some other reads and writes that synchronize with each other, need to tell you by logic that you observe certain values. So you can't ask anyone, like, what is the total order? It's an implicit order, but it's going to be one total order. You never know what it's going to be. It's like committing to a database. All the transactions can go in some order, but they are going to be atomic and have some order in the end, if you apply like a sequential consistent transactional behavior, which you don't need to do. So this is what sequential consistency does on top of acquire release. And there's no distinction between writing and reading values. Sequential consistency is a memory order that applies to stores and loads. So once you load a certain value, you for sure can never go back, but it also restricts from seeing much older values from other atomics. Does that make sense? Yes? Does the sequential consistent load guarantee that your other writes to memory become visible to other threads? No, because a load does not synchronize with another load. So you can't pass data by loading something, even if it's sequentially consistent. Okay? Cool. So how can we break that? I couldn't really come up with an example that specifically shows breaking acquire release and make it work with sequential consistency in the way that we pass data. But there's some optimization that all the CPU do that makes a difference observable in sequential consistent behavior and acquire release behavior. This particular optimization is true even for the strong consistency memory models in hardware. So all the CPUs basically do this, but only if they are built in a complex way. And what I'm talking about is some out-of-order execution where we read a value after storing something else. And as discussed before, storing a value will only make visible your writes that you did previously, but it does not prevent from loads that happen to be later in the program to be done prematurely and be ordered before writing the data. And writing data to memory is a really slow operation, which is why we try to go on in the program for as long as possible, even if the written value is not yet distributed to other subsystems in the CPU. Okay? Yeah, so the slide, well, we talked about this. All sequentially consistent operations have a total order. Okay, this is also one of the popular examples on how to break concurrent things. We have two shared variables, x and y, and we have two threads. They basically do the same, but reversing the variables. So one is going to write into x, and the other one's going to write into y, and then they read from the other variable. And if you first think about it, however you interleave these instructions, you should not come up with any way to end up with R1 and R2 being 0, both at the same time in the end. Right? Hopefully. So any one of the writes needs to go before some of the read. And you're going to observe at least one of the ones. So does everybody agree with that? Yes? Is load intentionally missing memory order? No, it is not. Yeah, which like memory order can we apply? I'm talking about variation between relax, acquire, release, and sequentially consistent. So the loads should be the same memory order. Thanks for pointing that out. So what will happen? Yeah, most of the time it's going to fail. If you really push it and make these examples hopefully be executed at the same time in different cores of your CPU, what's going to happen? If we apply relax semantics or acquire release, from our logic of the program, it shouldn't really matter, but it matters in hardware because we can observe that reads are ordered before the writes. So going back one slide, in each of the programs, there's first a write and then a read. And the CPU will come to writing some value, which will take a considerably long time. And during this time, it's not going to lie dormant, be idle, but load data that is specified in the next instruction. But only if the CPU is sufficiently complex to apply this reordering. So unless we apply sequentially consistent ordering of both stores, both stores need to happen in some certain order. We don't have an order, and the order can be different for both threads. And this is what's going to happen. They both read the old value of yet the other, respectively, the other atomic variable. Unless we apply sequential consistency, which gives a total order to both the stores and the reads, which is going to introduce some instruction in your program, which is going to take a long time to execute because it's going to wait on writing data to memory, which you usually want to avoid across all cores, across the whole system. All right? It turns out that on ARM, because it's much simpler CPU, it's probably not going to reorder instructions in this sense, but well, I put up rare instead of fail because it would fail 1 out of 1,000,000 times, where on Intel it would fail like 10% of the cases. I don't know, it's just the measurement. Maybe it's still distributing data throughout the memory system because it doesn't have strong ordering. It fails, but maybe not for exactly the same reason as on the Intel. Yeah, the comment is that even if it doesn't reorder the instructions, it's going to issue the writes to do different FIFOs to be written to memory, and then It's the memory system not being fast enough to distribute the data to the other core, and then you observe the failure behavior. So this is kind of like a warning that whatever memory order you apply, you need to be aware of stores only releasing writes, and there could still be reads be ordered before that. Make sense? Cool. Then, to recap this, what have we seen? There's no unique total order across all the atomics, because we still want the parts of the program to be independent if they operate on different atomics. So only per atomic there's a total order. And the memory order we apply on operations of each atomic are going to influence the reordering and optimization at various stages of program execution. The optimizer may reorder, the CPU may reorder, the memory might be distributed in certain ways that make things appear in different orders. And then these memory orders impose different restrictions on which writes to other memory become visible to your consumers or acquiring readers or relaxed readers. So in the end, don't try to avoid atomics. Try to let other people do this and use whatever, message queues or something else. Maybe use a mutex in the beginning and make your program work in the first place before trying to be clever on making it faster, because it's much easier to make a working program faster than a fast program working. And think of the order guarantees if you actually need to apply atomics, and if you need to port your code to different hardware, be aware that different hardware may run your code in different ways. All right, thank you.